Here we have an Automation Direct GS1 variable frequency drive powering up a small three-phase induction motor. And what we have set up right now is a configuration of the drive and a connection to a loop calibrator that is sourcing 4 to 20 milliamps into the analog input terminal of the drive. This allows us to do speed control of the motor using a 4 to 20 milliamp signal. So right now 4 milliamps, which is 0%, gives us 0 speed. If I move this to 8 milliamps, you can see in here the motor begin to turn, and over here we actually get some speed on our display. If I go up to 12 milliamps, this is 50%, running at half speed. Now we have 16 milliamps, which is 75%, 3/4 speed, and 20 milliamps, which gives us full speed, in this case a little over 60 hertz. So the motor is running at full speed right now. So we have control over this motor using a milliamp signal. Now, right now, the source of our milliamp signal is this Fluke Model 772 process loop calibrator. However, it doesn't have to be this way. We could have this milliamp signal come from the output of a PID controller, for example, or a handset, a loading station, or an operator control panel. That way, if it's a PID controller, the controller can tell the motor how fast to go, as opposed to telling a throttling valve how much to pinch off the flow. Usually it's much more energy efficient to change the speed of the motor as the final control element rather than having a pump or a fan go full speed and to throttle the flow using a dissipative type of valve. Much more energy efficient this way. So we have the ability now to use a induction motor, a standard induction motor, as a variable speed final control element for any control loop that uses 4 to 20 milliamps. And here we're just simulating the 4 to 20 milliamps using this handy loop calibrator, just to show the principle. Very cool stuff.